Hello everyone, welcome back. We are moving to a new chapter again. So today we are going to talk about the non-linearity of the regression models. So in chapter 7 here, we are going to talk about how we can move from a linear regression model to a non-linear form and trying to make the model a lot more flexible in order to achieve a better predictions capability. So today it's a very simple demonstrations on the polynomial regressions and the step functions. So we will move into a more abstract, sophisticated models, which is the regression splines and the smoothing splines models in the next videos. So today just basically a warm-up for you guys, and some of this stuff you already have seen in the previous videos. Alright, so let's not wasting too much time here. Let's start with our example here. So today we are going to use the wage data sets from ISLR library. So we will first call out the ISLR package, and we will attach the wage data sets. Again, if you are not sure about what is in the wage data sets, you can always ask. So here, the wage data set has, of course, the variable year, basically the year of wage information recorded, and age of the worker. We have a factor levels, marital status, race, educations, regions, job class, health, insurance, log of wages, and of course the raw wages here. So those are the things we have. Of course, mainly today we want to try to use a very simple example here to demonstrate the use of polynomial equations, right? The polynomial regression models, and also a step functions for both regression models and also logistic models. So we are basically attacking the regression problems and the classification problems using the same technique, so that you can actually see how we can apply this non-linearity models on the two problems. So we first begin with reviewing, right? So using the LM functions to basically build our polynomial equations. So again, if you are not remember how to do this LM functions, you can always go back to the previous videos, right? So we already talked about. So in this case, we are having a response variable wage here. And also we are going to add our first variables, the predictors, in our equations, which is age. And then we want to actually add a second term here, and the second predictor we're going to use its age square. And then we want to add one more here, which is age to the cubed. And then the last one right here, it's age to the fourth power. So keep in mind, when you actually passing in the power terms into your regression model, the LM functions, you have to always remind yourself to use the I wrappers. So this I wrapper is going to give you the power forms in the regression model. Without specifying this I wrappers in the LM functions, unfortunately, you won't be able to run the functions as you want it. So just something to remember in terms of the syntax. So we have all the predictors put into the model, and we are going to use all the data in wages, right? So this time we're not doing cross validations or bootstrapping here. We're just running the model with all the data points in the data sets. So we're going to fit the models, and you can see how the summary, right, outputs from this polynomial regressions. So we have age, a squared, age to the third power, age to the fourth power. Well, instead of using this very traditional ways of writing the formulas in the linear regression models, you can also use one particular shortcut right here. So there's another wrapper. So it's called poly. So you can actually pass in this poly wrapper into a LM functions to identify what is the degree of polynomials you want to use in your linear regression models. So the way how we do it, it's similar, right? So we have the response variable wage, and it's going against this polynomial term. And in this polynomial formula, we have only age, right? So age is the one we pass in, and we want to have 4 degrees of polynomial. So 4 degrees basically means we have age to the first power, age to the second power, age to the third power, and age to the fourth power. And here, well, it's worth to note that we have this argument here, raw equals true. So the arguments here basically allow us to run the regression model fits, and also reporting the true coefficients or the effect estimates for the model. So I will do a demonstration without the arguments raw equals true, because the default is equals to false, and see what happens, and I'm going to explain the difference between the two. So let's run this model pretty quickly, and then we print the summary. So here we have a polynomial equations with intercepts, right? So the first degree of h, which is h to the first power, h squared, h to the cubed, and h to the fourth. So if you compare the coefficients here, right, so for each of the variables to the previous, obviously everything looks the same, right? Because why? Because we are basically building exactly the same model, but just using a different syntax here. So now, as I told you earlier, because when we actually putting the arguments raw equals true in the linear regression model functions, the model will have the fits that reports the estimate coefficients, which is the effect of each term to the response variable. However, the coefficients for each term, if you do not put the arguments raw equals true into the polynomial term, unfortunately the coefficients will not be able to will not be the set of coefficients that we use to basically put our interpretations to the model. So let's try this, right? So we're going to run the model without the arguments raw equals true in the polynomial wrapper, and we are going to print the summary here. So the only thing that's fortunate is all the p-values, it's very consistent to our previous results, right? So they are basically all statistically significant. However, as you can see, each of this term here has a very, very extremely different coefficients, right? So the beta 0, beta 1, beta 2, beta 3, right, and so on. And you might ask, why are they different, right? So what's the difference here between the two models? So in a simple case, we actually call this the orthogonal polynomial functions, which essentially means that each columns that we use to pass into the model, it's basically a linear combinations of the variables itself. So that's why when we actually passing this parameters into, or this polynomial powers into our LM models, the outputs will not be the same as the previous suggest. So just keep that in mind when you are using a polynomial functions or wrapper in a linear model. Make sure you report raw equals true in the arguments, so that you're getting a coefficients that you can interpret in the orthogonal polynomial forms, unfortunately, only the p-value can be interpreted, but not the coefficient. The coefficient has a very different meanings. And in most cases, you don't actually need to interpret it because it has no meaning at all. All right, so the next thing we want to do is to see how well the model fits, right, to our data. So in order to actually create visualizations for the fits, we would like to first break the ages into a little grids, right? So we want to actually have the age put into smaller intervals so that we can actually pass in the age values into our models so that we can make a predictions for each groups of ages, right? So that we or each age, right, values in our data sets. So we would like to create a grid. So we are going to first use the range functions here to define the range of age. So here you can actually print out what we have here, right? So the age limits. So you can actually see that we have the age limits here, which is from 18 to 80. So the next thing we want to do is basically chop them up into a sequence. So we use the sequence functions here and to divide them into a grid. So again, so you can actually try to print this out and see what it is. So we have basically segment out a value 18 to 80 to a individual intervals here. And then what we want to do is to run a predictions. So this time we are going to use the fit polynomial models, right, that we actually built here, right? So using the polynomial wrapper, and we are going to pass in the data for our predictions. So this time we just want to plot age 18 to 80. So we want to see how each of this age will give us a predictions from our model. And we also want to report the standard error in this predictions. So this is something new that you haven't seen in the previous. So in the predict functions, it actually very convenient for you to actually pass in this argument here, SE, which is which stand for standard error, and equals true means, well, it will report the standard error. So it will store everything into this predict value here. So let's see what we have. So we store the predictions and we see what the assigned values. So in the assigned value, usually you only see the fits, the value, right, returns. And now we have the standard error of the fits, we have the degree of freedoms, and we have also the residual dot scales. So if you are not sure what it is, again, well, don't feel shy. You can always print it out, right, by just defining it, right? So run it. So this is the return values. So again, you have the fits for each category, right? The age category, right? The first one is age of 18. The second one is age of 19. The third one is age of 20, and so on. And you also see the standard error, right, for each age in our predictions. So in the age of 18, we see a very big standard error, and in the age of 19, we see the error gap narrow it down, and then we see a better and better result as we move to a higher age range. But as we move to a higher and higher age range, seems like the standard error starts to expand again. So that means the model that we build can only do a very good predictions for the age groups in the middle, not so well on the two end of the age range. All right, so again, well, we're trying to plot this fits of the model to the data, and also we want to see how the standard error, right, looks like. So we will first create a standard error band here. So what we are doing is using the fits of the from the prediction models, right? So from the predictions, we are basically having the fit plus 2 times the standard error of the fit, and then we have also another lower bound right here, which is using the fits of the model minus 2 times the standard error of the fit. Again, this will create approximately a 95% confident intervals, standard error bands for our plotting purpose. So let's store this band, and then we can actually plot them. So first of all, I would like to plot the age and wages from our data sets. So this is how it looks like. Oh, seems like we have some very scattering plots right here. Doesn't seem like there is an obvious pattern, and we would like to see how our model suggests for the predictions. So we have the line right here. So we want to create a line, and we are going to use the age.greet, which is the number of the age, right, from 18 to 80, which is the range, right? So we have every single value there. And we would like to plot this line against the fit of the predictions that we run earlier. And we will create some criteria here, right? The link width it's 2, so make it a little bit obvious to see. And then we would like to use a blue line right here. So let's plot this. Okay, so now we have the visualizations of our fitted lines. And the next thing we want to do is to plot the standard error to see, well, how well it make predictions for our data sets. Right? So how well this this model is actually predicting the values. So we would like to have another lines, but this time we are going to use a matte line right here, so which is kind of like a dotted lines. And we would like to again use the x-axis, which is from age 18 to 80. And for each value, we have a standard error band that we calculated earlier. And then again, well, this standard error band has 2 values, right? So one is the fit plus the 2 times standard error, and then the other value is the fitted value minus 2 times the standard error. And I would like to use blue color again. If you don't like it, you can actually use a red color if you want to make it a little bit more dynamics to see. And here we have the parameter or the arguments here, LTY equals 2, which is used for broken lines. So let's see how it looks like. Okay, so it seems like a very, very nice visualizations to show how well your model is actually making predictions for different ages. Again, this line is not the one that we use to demonstrate the training model. We're basically using the training model to fit the value of 18 to 80 so that we can actually plot out a line to see the behavior of the models. So this is basically the model trained with all the data that demonstrate the predictions of each age in our demonstrations. So again, well, the whole idea for this demonstrations here is to evaluate how well we are doing, right? So we can also try to run this ANOVA test to see how well the model actually do if we have a different polynomial degree. So let's run this model fit here by basically defining we have wage against education, age against education and age, wage against education and age, and then wage against education and age to the 2 polynomial degree. So that means with age and age square. and then educations and age to the 3 degree of polynomials, and then 4 degree of polynomial. So now we have one additional predictor to pass in here in this model with different polynomial forms. So we want to know how well they are compared to each other, right? So overall. So one way to do this is basically using a ANOVA test. So if you are not familiar with the ANOVA test, or you have never learned this in your basic statistics class, an ANOVA test, basically it's a test for variance that allow us to do comparisons of multiple statistics in one calculations. So unlike the t-test, right? So the t-test allows you to do comparisons of only 2 conditions. However, the ANOVA test, it's similar to the t-test purpose, but then it allows you to make comparisons of multiple conditions. So this time we have 5 different models we want to compare, and we would like to use the ANOVA test. And if you are not familiar with the ANOVA test, let me give you a hint here. So remember the regression model that we learned previously always report a F values. Remember there's an F statistic that you see from the outputs. So what is the F statistic? So the F statistic, it's basically an ANOVA test that testing against the current model, compare it to a model where all the coefficients, the betas in our model equals to 0. So if you actually think a little bit more about it, well, so the ANOVA test, it's basically used all over the place. So in this case, well, we are not comparing to an empty model, right? So where all the beta equal to 0, we are actually comparing how model A to the performance of model B, and how model B to the model C, because, well, they contain different variables, right, predictors in the model. So let's see what returns from this ANOVA test comparing the 5 different models here. So in this case, we have a returns result here. So the result suggests we have the second model here, which is statistically significant. So what it means is basically the second model, which is the one with age, is superior over the basic model. The base model, it's basically the first model we have, the one with no age in there. So that means, well, if this second model is statistically significant, that means it comparatively to the first base model, it's very, very statistically significant. And if we are going to look at the second result here, so the second result also statistically significant, that means, well, when it compared to the third one, comparing to the second one, well, we also get a better result. It's statistically different. It makes an improvement, right, of the model. So that's why it's also better. So that means, well, the third one is superior than to the second ones. And the fourth one also is superior to the third ones, even though in the statistically significant level, it's not as high as the previous, but then, well, still statistically significant, suggesting that, well, in this case, at least less than 5% of a chance that we will get wrong, right? So that's pretty low error rates here. And the last one, so the last one is extremely insignificant. So that means, well, the adding the fourth power to the model, it's not anything better than the previous models. So that means, well, they are almost the same. So if they are the same, then, well, why are we even actually putting a more complicated model? So in this case, by comparing the models with ANOVA test, we are able to tell what level of polynomial degrees that we should use for our polynomial regressions models. So the next thing we are trying to do here is to use our logistic models to prove that we can also apply the same polynomial format, right, to make it more nonlinear for making a predictions of the probability for true and false, right? So a binomial terms, right? So logistic function is a very good classification tool for making a binary choice So here, what we're going to do is to use the GLM functions. So again, well, you should be very familiar with it by now. So here we define the family equals to binomial. Basically, it's going to suggest we are using a logistic regression models here. And we have the wage as our response variable here. Again, this time we are using a I wrapper here to define what is the range of the wage data we want to use for our binomial choice. So anything that is above 150 will return true, and anything, of course, below or equals 250 will be classified as a false, right? And this response variable will go against the polynomial term here using a degree of 3. Since we find out in the previous ANOVA test, degree of 3 help us to do a better model fits in the regression problems. So we might as well to use it for a logistic problems or a classification problems. So we're using datasets wage, right? We're using everything. We're not using just partial of it. We're using all the data. Let's see what it comes up. So here's the summary of the tables of the models. So in the regression, in the logistic models, we actually find that the third degree here is actually not statistically significant. But the second power and the first power, it's actually very statistically significant here. So you can basically try to make a predictions just like how we did in the previous case. So in this case, we are trying to make a predictions from our logistic model. And again, we are using the age grids that we produced earlier, right? So we are trying to make predictions by each age we have in our range of data, right? From the age of 18 to 80. And again, we want to actually report the standard error from our model's predictions. So let's run this to make a predictions for the logistic model. And again, well, you want to see what returns. Those are the 3 things returns. So unlike the regression model's predictions, the logistic binary choice problems will only return with the fits of the model, the standard error of the fits, and also the residuals. So here we are going to make the standard error band, right, similar to the previous. So we are trying to basically use the logistic fits, plus we are using a C-bind right here, fit equals to 0, and the lower bound here equals to -2 times the fit, and the upper bound here is 2 times the standard error of the fit. So it's just another way how you can do the calculations of the plus and minus boundary, but it's your choice. If you want to use the previous methods, it's totally fine, but here, this is what we're going to use. So we can actually see the first 5 results, right, returns here. So the first 5 results return the fits from the model, age of 18, age of 19, age of 20. And the lower bounds of the predictions, the upper bounds of the predictions. The lower bounds, the upper bounds. All right, so now we created boundaries here. So we want to actually calculate the probability, right? So we want to know the probability. So we have to actually make a probability band here from our standard error band. Remember, logistic model is not a linear model. You have to put it back into a logistic equations to calculate the probability. So here we have the exponential functions to the SE dot bounds, All right, so the boundary, upper bound, lower bound, divided by 1 plus the exponentials to the upper bound, lower bounds. Right, so we should actually return 2 columns from this, actually 3 columns, because I do have the model fit right here, right, as the first columns. So we will put in this number here into the logistic equation and calculate the fits probability, and then it will put this number here to the logistic equation to calculate the lower bounds probability of the model for age of 18, and then it will put in this number into the logistic equation to calculate the probability of the upper bounds. So let's see what returns here. So here goes. So we have all this probability returns. So those are the probability for age of 18 to be true, which is have a high wage. This is the lower bounds, which is extremely small, right? So we have the upper bounds of probability, which 1% of a chance that a person who is age of 18 will earn a age over 250. So again, well, you can continue to interpret this. Again, I don't think interpreting the number from a table is a good idea. So why don't we actually plot the number out? So we are using the matplot functions here, and we are putting in the age grids, and we are making the probability bands here, right, which is the result from here, and we are using column. The color equals to blue, or maybe this time you can you can use different color. Let's say if you are interested to use, I don't know if green is going to stand out, but let's use green. And then the width of the lines, right, and also all this parameter you can pass in. So let's plot this. So here it goes. So this is basically the graph that shows you the probability for different age groups to get a high salary range. And it doesn't seem like, well, there is a lot of the people can actually get to the high end of the wage. Well, if you are confused about this, you can probably think about, well, why does that happen, right? So you can actually basically ask the question, so what is in wage, right? So let's say we want to see the range of wages. So let's see, wage as a small w. So the wage actually range from 20 to 318. So 250 seems like a middle point here, but it's not necessary that we have a lot of people in that range, right? So let's say if we want to know how many people are there, so we can actually see I equals, or maybe we can actually do the distributions of plot wage. So we can see that here, right? So this gives you a very good demonstrations. So we have a very clear cutoff here, 250, where there are not a lot of people actually on the upper range right here that it's above 250. But there are huge populations, it's way below it. Then obviously now you can tell why we have such a problem, because when we are actually trying to model this with the cutoff of 250 or above or below, we are actually putting a huge groups of people or observations into a lower range where majority of them will be having a very low chance to actually earn that high wages. But there will be a small tiny little groups scatter different age groups that we cannot even tell whether one is earning more. But one thing that we know is it kind of spiked up here at the age of 40 something to 50. This is the the range where you see the people in this range, they will have a higher probability to earn a higher salary. All right, so the last thing we want to go over is doing the step function. So again, if you went through the lecture we finished, you should know a step function. It's basically cutting the range of our predictors into different sections so that we can get the average of this range of observations by the cuts, right, by that sections. So to do the step function, to be honest, it's not difficult. We're basically just building a linear functions here with a constant. So if you are interested in how we do it, you can actually first ask what is a cut functions. So cut function is basically the way how we convert number into different factors. So we want to actually create a new dummy variable, right, in our linear models to define the range of that cut. So we can actually create a cut by using this cut functions. For instance, let's say we have a range of age from 18 to 80. And if we want to actually cut them into 4 bins, right? So we want to cut them equally into 4 bins, you can use the cut functions here. And I'm going to demonstrate, well, what it looks like. So the cut function will give you a range or interval here, something that is from 17.9 to 33.5, which is inclusive. This one is not inclusive, so 33.5, it's less than 33.5. Anything 33.5 or equals to 33.5 above or equals will be in this interval here all the way until 49. And then from 49 equals or larger to 64.5 will be here. And for each intervals, you can see, well, how many observations you see in our data sets. Right? So that's the total number of observation from each interval, each beam. So again, well, this cut function can be passed in as a wrapper, right? Just like the I and also the poly functions. So you can also use this in a linear models. So what we're going to do is to use the linear model, going with the age. Again, well, this should not be age, but it should be wage. And then we use the cut functions, right? So we are trying to predict wage, and we can use the cut functions, and we cut it up, the age, into 4 bins, and then we pass in the data sets here. So let's see how it looks like. So we're going to print the summary. So here it goes. So as you can see here, we have a very nice return result here. So we have the second bin right here and the third bin right here, which are statistically significant. But the last one right here is not so well because it's not statistically significant. And obviously, you might actually ask the question, hey, how come one of the 4 groups actually missing? So yes. So in this case, when we're using a cut functions as a wrapper in a linear model, what happens is it will always treat the first groups or the first beam, right, being cut as the base group in our model. So remember, when we're creating a dummy variable for a categorical predictors, what happens is you do not pass in all the predictors, the dummy predictors, into your model. You have to always leave one group out as your base to compare. So in this case, well, what it means is we have this 94.158, which give you an idea. If you have a age groups that it's not belong to 33.5 to 49, it's not belong to 49 to 64.5, and also it's not in the group of 64.5 and 80.1, then obviously the only thing that you can understand is it should be belongs to the group where is 17.9 age to 33.5 age. So that means when this dummy here is 0, this is 0, this is 0, and you know that the average wage for the people in the age group of 17.9 to 33.5 should have an average age of, or average wage of 94.158. So creating a step function, it's not difficult at all in R, and in fact it's actually quite intuitive. And also, if you are interested to create your own grids, right, your own cuts, you can also use the cut function. So again, well, table function is not necessary, but you can actually display the cut here. So for instance, you can actually define the range you want to cut this interval. So for instance, you can define with a vector. So let's say I want to have the initial group right here, 17.9, just like how we did. And I don't like the first range go only up to 33.5. I want to go to 35. And then I want the next range goes to 50. And I want to go the next range boost to 65. And of course, the last group right here, it's anything that is inclusive to 80.1. So let's see what it turns out. So it turns out that we have a cut right here that it's completely in my control. So unlike the previous, right, the previous it's automatically chopping or cutting the data into a quartiles of the age. But this time what happened is I am actually taking full controls of how I want to segment my age groups in this step functions. So I would strongly recommend you guys to take a little time to practice, right, with this code and trying to understand how you use these polynomial functions and step functions for your projects or maybe for your assignments too. So today we are covering two very basic nonlinear functional forms here, and we will move on to the more abstract and sophisticated model in the next videos. So I will see you guys next time.